Hello and welcome to this video for mechanics of deformable solids. So in this week we are going to start a new chapter. So we are continuing to see different types of deformation, and for different types of deformation our objective is to understand how the external forces or external moments that are applied on a given member will induce a stress and a deformation. So in the previous chapter, we saw the case of axial load, where we saw what is the deformation, the elongation of a material that is either subjected to some external normal forces along its longitudinal axis, or some changes in temperature. In this case, we saw how to calculate the elongation of the material, so the deformation, but also how to calculate the normal stress to estimate the risk of fracture of this material. So now we are going to see in this chapter for this week a new type of deformation, which is going to be, in this case, the case of torsion. So what is torsion? So let's start with defining what is torsion. So to illustrate what is torsion, so let's consider a shaft like this. So let's consider that you have a cylinder like this that is attached to a fixed support at one of its extremity. And then you have a torque that is applied on this cylinder. So what is a torque? A torque is a moment that is applied along the longitudinal axis of this cylinder. So it's a force, a moment that will tend to make the cylinder twist along its longitudinal axis. So that's how we are going to define torsion. So torsion, we are going to define it as a twist deformation of a member that results from the application of a torque along its longitudinal axis. So in this case, X would be, in this case, the longitudinal axis of this shaft. And in this case, the moment is applied along this longitudinal axis. And in this case, when you have a moment that is applied along the longitudinal axis and tends to make the cylinder twist, in that case we would call it a torque. So we would typically write it T, and in this case that would be a torque. So if you think about what type of deformation torsion will do, so if you consider a cylinder like this before deformation, and let's assume that you have a cylinder like this, and that you have some kind of grid that is printed on this cylinder. So you have a grid like this, where initially this grid is made of small little squares like this. So you have a square grid along this cylinder. So before the deformation, this grid is made of a small little square like this. And when you think about what this cylinder will look like after deformation, then the effect of the torque will cause this cylinder to twist. So if you think about what this cylinder is going to look like after the torsion deformation, the lines of the grids that are on the surface of this cylinder will now look like this. So you will now have a twisted cylinder like this, and so this is what its surface would now look like. So now if you consider what type of deformation and what types of strain and what type of stress this cylinder will undergo, so if you look at the distance between the lines of this grid, here the distance is not going to change due to the torsion. This is because when you put a cylinder under torsion, this is not going to compress or elongate this member. The length of this member will remain the same. Unlike the case of axial load, a torsion will not change the length of the cylinder. What will change, on the other hand, is that if you look at the little square that are on the surface, now after the deformation they will not be a square anymore. They will have the shape of a diamond, which means that if you look at a little square that is on the surface, initially it will look like this, and after the deformation this little square will now look like this. And so what this means is that what used to be a square at the surface will now look like this kind of diamond shape, which means that you have a shear deformation that will be applied to this cylinder. If you look at here the fact that initially you have a square, what doesn't change is the distance between the line, but what changes is the shape of this square. The shape of this square is changing. The square now becomes a small diamond. And so if you have the distance that are not changing, but the shape that is changing, then it means that you have a shear deformation that will change the shape of the surface. So in this case, the thing that we are going to derive in this chapter is that torsion does not induce any normal strain or any normal stress, because the diameter of the cylinder and the length of the cylinder will remain the same after torsion, so there will be no normal stress and hence no normal strain. But on the other hand, what we see here is that the shape of the surface is changing, so there is a shear deformation. So torsion will not induce any normal strain, but will induce a shear strain at the surface and inside the cylinder. You will have a shear strain. And if you have a shear strain, then due to the Hooke's law, you will also have a shear stress. So what we will see in this chapter is two things. Is first, for a given torque, an external torque, can we predict the deformation of this cylinder? So the deformation will be defined by its twist angle. How much twist angle can you make for this beam? And so that's the deformation. And the second thing will be to calculate how much shear stress is induced in the member due to the torsion. So if we can relate the external torque that are applied to a given shaft to the shear strain and the shear stress that is created within the shaft, then if we know the shear stress, then we can calculate its risk of fracture. If the shear stress exceeds the ultimate stress of the material this beam is made of, then there is a risk of fracture. So those are the two things that we are going to do within this chapter. So to calculate the deformation and the stress that is generated within a shaft that is subjected to torsion, just like what we did for the axial load, the first thing is that we need to find a way to estimate what will be the internal load and the internal moment within the shaft. So we need to find a way to calculate the internal load and internal moment as a function of the external moment and external forces that are applied to this shaft. And then once we know those internal force and internal moment, then we will use this to calculate the internal stress and the deformation. So for this, we first need to define what are the internal load and internal moments within a beam that is subjected to torsion. And in the case of torsion, again, what will matter is not the, for example, the normal, the actual force or the shear force, because there is no normal force or shear force that is generated by a beam subjected to a torsion. What will matter in this case is what is the internal torque within the beam. So since you are applying an external torque to this beam, what will matter is within this beam, what is the internal torque that is undergone by this beam within its bulk. So for this, just like what we did for the internal normal load, we need to design a sign convention. We need to decide what will be the sign convention for the internal torque. So let's take an example for this. So let's consider a given shaft like this, and let's assume that it is subjected to some external torque. So let's consider the cylinder here. So let's assume that it is subjected to some external torque. So when I'm going to draw the torques here, I'm going to always use the same convention. So here, when you draw some torques, you need to be careful, because a torque is something that is three-dimensional. It's something that is twisting the member along its longitudinal axis. So when you draw the torque in 2 dimensions on a piece of paper, then you need to be careful how you draw it. So in this case, what I'm going to do when drawing torques is that I'm going to draw the torque using a solid line like this, if it's a torque that is coming towards you, that would be above the piece of paper, above the plane along which I am drawing this schematic. And I'm going to draw a dashed line if it's the torque would go below the piece of paper, if this circle is going below this piece of paper. So in this case here, it means that the direction of the torque is a torque that starts below the piece of paper and then comes towards you and then go above the piece of paper and then come back. So here in this case, if you look at the projection of this torque, if you put your right finger, your right thumb towards the positive x, so towards the right, then the direction of your finger would give you here the direction of this torque. So it would be a torque here with a positive projection towards the x-axis. On the other hand, if I draw a torque like this with a solid line like this and with a dashed line like this, then it's a torque that would have now a negative projection along the x-axis. So this is the sign convention that I'm going to use. It's important that you are careful when drawing torques to avoid ambiguities of when you draw them. So because the way you draw them depends on some perspective. It depends on if you draw this three-dimensional shaft as looking at it from the right or looking at it from the left. So for example, just to make it clear, now if I change the perspective on this thing, so now I draw the same shaft, it's the very same shaft, but this time instead of looking at it slightly from the right, I look at it slightly from the left. So if I want to draw exactly the same external torque, now this torque would be starting below the piece of paper like this, and then would come back like this. And again, if you put your right finger, your right thumb towards the positive x, you can see that this is actually the same torque here and here. So despite the fact that it looks different when I draw it, this is exactly the same torque that is having a positive projection onto the x-axis. So a torque that follows the right hand rule, the direction of your finger, if your thumb is pointing towards the right axis. And on the other hand, now if I look at the torque on the other side, so this would be a torque that would come like this. So again, this would be a torque that this time has a negative projection on the x-axis. So you see that if you, when you draw the torque in 2 dimension like this, or when you project a torque that is a 3-dimensional thing onto a 2-dimensional piece of paper, you need to be careful the way you draw it so that there is no ambiguity whether it's a torque with a positive projection like this one, or a torque with a negative projection like this one and this one. So again, to avoid any ambiguities, I suggest you follow also this convention of you drawing on the dashed line the part of the torque that is below the piece of paper, and then in solid line the torque that goes above the piece of paper. So once we agree on this, so now let's consider that this torque is, so you have those two torques that are applied on both sides of this beam. Necessarily, we know that this beam has to be at equilibrium. So if you have a torque that has a positive projection on the right, then there has to be a torque with a negative projection on the left to counterbalance those two torques, so that the sum of those two torques is 0 for this beam to be at equilibrium. So again here, since we want to be able to calculate what will be the internal torque, we need to define a sign convention. So for this, if we want the internal torque, just like anything that is internal, we need to use the method of section. So we are going to take a given position x on the x-axis and cut the beam into two parts at this position x. So then after we cut this beam, we can either isolate the left or the right. And in this case, so if we isolate the left, then we have the beam, the fraction of the beam let's assume that this beam goes between x equals 0 to x equal L. If we isolate the left, then we have the fraction of the beam that goes between 0 to the specific x at which we are cutting this beam. And if we isolate the right, then we have the right part, that is to say, the part of the beam that goes between x and L. So in this case, if we want to calculate the internal torque, so you would have the external torque here and here. This is the external torque. And in this case, so we are going to define the internal torque within the beam in the same way that we define the internal load. We are going to define the internal torque as being the torque that is applied from the right to the left or the left to the right. So we know that in this case, if we cut the beam into two parts at a given position x, the right side is going to act as a fixed support to the left side or vice versa. So which means that there can be potentially a torque that is transmitted by the right to the left or the left to the right. And this is going to be the internal torque. This is the torque that is applied by the right part of the member to the left or vice versa. We know due to the principle of action-reaction that the torque applied by the left to the right is the same but equal sign than the torque applied by the right to the left. So here we need to define a sign convention to define what is a positive torque and a negative torque, so that we always find, so that we have a consistent definition for what is the torque. Again, we know that the internal torque is going to be opposite direction, whether you consider the torque applied by the left to the right and the torque applied by the right to the left, due to the principle of action-reaction. So we know that necessarily one will have a positive projection along the x-axis and one will have a negative projection along the x-axis. So we need to agree on what is the sign convention. Just like when we said for the internal load, we always define it as pointing towards the outside. Then if it's always pointing towards the outside, then it means that when you isolate the left part, is going to point towards the right. And when you isolate the right, it's going to point towards the left. So here it's the same thing. We need to agree on a universal sign convention for the internal torque. And for this, the sign convention that we will be using is that if the torque is applied on the right surface, then we are going to define it as being positive if it's like this. And if it's applied on the left surface, then we are going to define it as being positive if it's like this. So the way to remember this is that in this case, we still use the right hand rule. In this case, what we do is that you have your right thumb as pointing towards the outside, and then the direction of the finger gives you the direction of the internal torque. So in this case, if you isolate the left part, then your finger, your right thumb would point towards the right, and in that case, the finger gives you the positive direction of the torque. Now, if we isolate the left surface here, now this time your finger will also point towards the outside. So in this case, your thumb will point towards this direction, and again, in this case, your finger would give you this direction for the internal torque. So remember that to get the direction, the sign convention for the positive torque is that you always have your right thumb pointing towards the outside, and then the finger gives you the direction of the positive torque. So in this case, again, remember to be very careful about the way you draw this internal torque, so that there is no ambiguity about whether you draw it with a positive or a negative sign convention. So in this case, if you look at this torque here on the right surface, when you isolate the left, this torque here will have, in this case, a positive projection along the x-axis, but on the other hand, this one would not follow the right hand rule if your thumb was to point towards the positive x. So in this case, this one would have a negative projection. And again, that's not surprising, because due to the principle of action-reaction, if the torque applied by the left to the right has a negative projection, then the torque applied by the right to the left has to have a positive projection, because due to the principle of action-reaction, those torques must be equal but with an opposite sign. So in this case, again, this is the positive sign convention that we will be using for the internal torque.